Welcome back to the Deep Dive, where we plunge into your sources and unearth the most fascinating, often surprising insights. Today, we're shining a spotlight on a group of professionals whose work is quite literally all around us, in every building we inhabit, but who often remain the unsung heroes. We're talking about the mechanical, electrical, and plumbing engineers. MEP.
That's right.
Imagine stepping into any magnificent building, be it a gleaming skyscraper, a bustling hospital, or even the comfort of your own home. Without these incredible professionals, these structures would be little more than inert shells. Beautifully sculpted, perhaps, but utterly uninhabitable.
Just shells.
They're the true wizards behind the walls, designing the vital organs, the nervous system, and the intricate circulatory networks that breathe life into our built environments, making them comfortable, safe, and functional.
Exactly. And our mission for this deep dive is, well, to pull back that curtain.
Yeah.
We want to explore the critical work of MEP engineers. We'll break down their distinct responsibilities, really appreciate the immense challenge of coordinating these incredibly intricate networks, and highlight their pivotal role, especially now at the forefront of sustainability, energy efficiency, and all the technological advancement we're seeing.
Okay.
And we'll be drawing from a really rich array of sources, from the ancient wisdom of Vitruvius and historical architectural texts, right up to modern project management guides and cutting-edge building information modeling handbooks.
Fantastic. So grab a coffee, settle in, and let's explore the essential yet often invisible world of MEP.
Yeah.
Level 1, the invisible infrastructure, bringing buildings to life.
Okay, so we often admire a building's visible attributes, its striking aesthetics, its grandeur, its soaring lines, or, an impressive facade. But I always wonder what truly makes it habitable and comfortable. What allows us to truly live, work, heal, and learn within its walls?
It's rarely the visible beauty alone, right? It's more that complex, unseen web of systems hidden from plain view, the very arteries, nerves, and respiratory system of the structure.
You've hit on a core truth there. Consider the profound transformation of a building.
Yeah.
It starts as a mere architectural concept,
Yeah.
maybe a beautiful sketch on paper,
Right.
and then becomes a truly living, breathing space. There's this great perspective in thinking in systems. Yanela Meadows talks about how a system's identity, its very essence, endures when its interconnections and purposes remain intact, even if the individual elements change.
Wow, interesting.
And MEP engineers are the ones who meticulously design and establish these critical interconnections. Without their sophisticated designs for heating, cooling, ventilation, power, sanitation, well, a structure is simply not a building in the functional sense that modern society not only expects, but absolutely depends on. It might offer shelter from the elements, sure, but it wouldn't meet those basic human needs for comfort, hygiene, safety, or the complex technological functionality we rely on daily. It's what turns a shell into a truly dynamic environment.
This sounds like a really stark contrast to earlier architectural focuses, doesn't it? Before modern conveniences, the idea of what a building was, it seems much simpler, less demanding on all these internal hidden systems.
Absolutely. The historical emphasis was quite different. For centuries, the focus was often purely on visible form, structural integrity, and maybe the sheer monumentality or symbolic power of a structure.
Right. The outside look.
Exactly. We're told Rybczynski, in Home, A Short History of an Idea, describes earlier houses that often lacked specialized rooms and certainly lacked the elaborate infrastructure for precise climate control or dedicated plumbing we just take for granted today.
A world away.
It really is. That's a far cry from today's multifunctional spaces, each demanding precise environmental controls and dedicated infrastructure for specific activities. Just think of a modern operating room versus a medieval dwelling.
Huge difference.
And Rainer Banham in Eccritic writes, he touches on this inherent conflict between sort of elite architectural preferences, which might prioritize pure, unadorned form and mass taste, which implicitly demands built-in equipment and user-chosen elements that enhance livability.
Function versus form again.
Exactly. And this distinction between the visible aesthetic design and the complex internal systems dictated by function, comfort, and user experience, which is the core domain of MEP, becomes incredibly clear. It highlights how these internal workings aren't just an afterthought. They're absolutely fundamental to how a space is actually used, felt, and experienced. They really define its very purpose.
It's easy, though, isn't it, to think of these complex systems as purely modern marvels, born from industrial revolutions and the digital age. But you're saying even ancient civilizations grappled with surprisingly similar fundamental challenges. providing water, managing waste, ensuring structural integrity,
Hmm.
just with vastly different technologies, obviously.
Yeah, and this really raises an important question about the deep lineage of engineering within buildings. It shows us how these essential, unseen functions have always been critical to human habitation. Take Vitruvius's 10 books on architecture, for example. It offers fascinating insights into early plumbing choices and a clear, almost startling understanding of material science from nearly 2 millennia ago.
Really? Like what?
Well, he details the dangers of lead pipes for water conduction. He actually notes how fumes from it settle upon their members and day after day burn out and take away all the virtues of the blood from their limbs.
Wow, that's incredibly specific. Lead poisoning, basically.
Exactly. This wasn't just a casual observation. It was a clear articulation of lead poisoning and a profound understanding of a health hazard long before modern chemistry. He then strongly advocates for clay pipes, emphasizing that the taste is better when it comes from clay pipes.
Oh,
He even goes so far as to point out that despite having exquisite silver vessels on their tables, people still preferred earthenware for the purity of taste in their drinking water.
that's amazing.
It underscores a long-standing practical awareness of how material selection directly impacts health and utility, a core tenet of plumbing engineering today. It's a striking reminder that the pursuit of safe and healthy infrastructure is, well, a timeless human endeavor.
That's a truly surprising level of detail and foresight from so long ago. Just shows a deep practical understanding of materials and their effects on human well-being. What else does Vitruvius tell us about these foundational, often hidden aspects of building that sort of laid the groundwork for modern engineering?
Well, Vitruvius doesn't stop at pipes. He delves into foundational construction aspects that we might consider direct precursors to modern civil and structural engineering, all with profound implications for what we now call MEP. He describes meticulous techniques for digging wells, requiring much acuteness and skill to the consideration of the natural principles of things. That indicates a thoughtful, almost scientific approach to acquiring and managing water resources.
Right.
He even issues chilling warnings about dangerous exhalations in unventilated areas leading to fatality.
So ventilation, even then.
Exactly. An ancient, yet precise recognition of the critical need for proper ventilation, a fundamental mechanical engineering concern today. And for structural foundations in marshy or unstable ground, he details laying charred alder, olive wood, or oak piles, filling the intervals with charcoal, and then laying solid construction atop them.
Complex stuff.
It really demonstrates that early builders, while undoubtedly focused on visible monumental achievements like, say, Zozer's Pyramid Complex, or the architectural intricacies of Wells Cathedral's strainer arches, they were equally, if not more, concerned with the underlying essential functionalities. These careful hidden choices were the ancient precursors to modern MEP, ensuring not just beauty and stability, but also basic habitability, safety, and hygiene for the occupants. Mine and two. Deconstructing the disciplines: mechanical, electrical, and plumbing.
Okay, so let's now truly dive deeper and unpack the specific, highly specialized realms of mechanical, electrical, and plumbing engineering. First up, mechanical engineers, they're essentially the master designers of a building's internal climate, right? Controlling everything from air quality and airflow to temperature and humidity. It's like the building's very respiratory and thermal regulation system, much more complex than just turning a dial, I imagine.
You've hit on a core truth. And what's truly fascinating here is how multifaceted their role is. It extends far beyond simply achieving human comfort. The Builder's Guide to Hot, Dry, and Mixed Dry Climates, for instance, it explicitly details advanced mechanical ventilation strategies. These are designed not only for occupant comfort, but critically, for year-round control of interior moisture levels.
Ah, moisture control. That sounds important.
It's crucial. This isn't just about feeling good. It's absolutely essential for a building's longevity. It prevents insidious issues like mold growth that can compromise health and structural integrity. They'll design for supplemental dehumidification using mechanical cooling, particularly crucial during cooling periods and part load conditions when the air conditioner might be running, but not effectively removing enough moisture from the air.
Right, that sticky feeling.
Exactly. The guide even specifies precise methods for attic ventilation, like ensuring half the vent area is near the ridge and half near the eave. There's even a practical rule of thumb: 1 square foot of net-free vent area for every 300 square feet of ceiling area.
Wow, that's specific.
Yeah, and this precise design helps to prevent moisture accumulation that can lead to wood rot or ice damming in cold climates. It's like the invisible battle against environmental degradation, preserving the very bones of your home or office for decades.
So, The true genius here isn't just about making a room feel cool or warm, is it? It's about a sophisticated interplay of air movement, temperature, and moisture control, precisely tailored to specific environmental conditions. It sounds like they're literally designing for the health and longevity of the building itself, like a body's internal organs.
Absolutely, you've captured it
Yeah.
perfectly. And their designs are fundamentally at the forefront of the industry's critical push for sustainability and energy efficiency. That's a key aspect of their wizardry. This includes implementing cutting-edge systems like radiant rough-in construction, where flexible cross-linked polyethylene or PEX, tubing known for its durability, corrosion resistance, and ease of installation compared to traditional rigid copper,
Right, I've heard of PEX.
distributes hot water directly within the building structure. As fundamentals of residential construction details, this tubing is embedded directly in concrete slabs on grade or fastened to the top or underside of good floors.
Seems efficient.
Highly. These systems are very economical, easily integrated with standard construction practices, and offer incredibly efficient, uniform heating that minimizes heat loss. So the choices made by mechanical engineers profoundly impact a building's operational energy footprint over its entire lifespan, significantly reducing greenhouse gas emissions and, crucially, directly influencing the well-being and health of its occupants by ensuring optimal indoor air quality and thermal comfort. They're engineering the very breadth of a building and its long-term environmental performance.
Okay, next, let's illuminate the nervous system of our buildings. Let's turn to the electrical engineers. These are the ones who literally bring light, power, and connectivity to every corner of a building, turning inert spaces into functional, vibrant ones. Without their meticulous work, even the most beautifully designed structure would remain dark, silent, and, well, largely useless.
Their responsibility is truly immense. It encompasses everything from the precise calculation of complex electrical loads for an entire building. I mean, considering everything from a single light bulb to heavy industrial machinery or huge data centers,
Yeah.
to ensuring safe, reliable, and efficient power distribution, and designing the intricate networks that bring life to every single device. Building Construction Illustrated highlights the service entrance, that's the crucial assembly, that safely conducts electricity from outdoor utility lines to the meter base inside. And then it emphasizes the importance of meticulously designed branch circuits to distribute power throughout the structure.
Branch circuits, okay.
Yeah, each circuit must be sized correctly to prevent overloading, ensuring both safety from fire hazards and efficient operation. Every 1-hour meter reading, every circuit breaker, every outlet, every single flicker of a light, they are all testaments to the electrical engineer's meticulous planning. It ensures that electricity is not just present, but safely and effectively utilized throughout the entire building, often supporting hundreds or even thousands of individual devices.
This is where it gets really fascinating, though. With the rapid evolution towards smart buildings and advanced automation, electrical engineering isn't just about providing raw power anymore, is it? It's about enabling intelligence, creating a dynamic, responsive environment. How is that intelligence actually woven into the fabric of our buildings?
That's the key question, and it's a profound shift.
Hmm.
If we connect this to the bigger picture, electrical engineering is the absolute backbone of the increasing technological complexity we see in modern construction and urban development. The City of Tomorrow, for example, describes how sensors, intricate networks, and integrated automation systems are fundamentally transforming urban life, and this is directly reflected within buildings.
Like smart homes.
Yeah.
Exactly. Smart home heating systems, which you can effortlessly control remotely via your smartphone from anywhere in the world, are now pretty common. These systems rely entirely on the sophisticated electrical infrastructure designed by these engineers, connecting countless devices, processing vast amounts of data, and executing commands in real time. And Designing Reality further expands on this, explaining how digital fabrication and programmable circuits are allowing for the creation of complete functional systems. This capability, integrating physical fabrication with programmable logic, is central to the rise of smart building controls.
Okay.
It enables dynamic, responsive, and incredibly efficient environments that can react autonomously to user needs, external conditions, and fluctuating energy demands in real time.
Yeah.
It's really about empowering the building to think and adapt.
And finally, plumbing, a system so fundamentally essential that we rarely think about it or even acknowledge its existence until, it's not working. This covers all aspects of water supply, drainage, and sanitation, touching upon pretty much every facet of our daily lives within a building. Plumbing engineers are truly safeguarding public health on a massive, often visible scale. Their work ensures the consistent delivery of clean, potable water for drinking, washing, and other uses, and equally important, the safe and hygienic removal of wastewater.
Absolutely fundamental.
Totally.
Hmm?
It's fundamental to public health and hygiene, preventing the spread of disease and creating sanitary environments that underpin modern urban living. Building Construction Illustrated gives a really comprehensive overview of these complex systems. It includes the meticulous design and placement of extensible plumbing fixtures like bathtubs, sinks, bidets, the intricate networks of sanitary drainage systems that rely on precise slopes, gravity, and venting to prevent blockages and odors.
Venting is key, I hear.
Oh, absolutely. And effective sewage disposal methods, whether connecting to municipal sewer systems or designing on-site septic systems. Their work guarantees that water, once sourced from wells or municipal supplies, is safely distributed throughout a building, and that wastewater is efficiently, hygienically, and safely managed and expelled without contaminating the environment or residents.
It really makes you pause and consider just how profoundly these engineers are safeguarding public health on a massive, silent scale. It's an often overlooked but incredibly vital contribution that we rely on every second of every day.
You're absolutely right. And the challenge lies not just in the sheer functionality of delivering water and removing waste, but in the intricate integration of these systems within the building structure, and crucially, in unwavering compliance with a vast array of regulatory standards and health codes.
A lot to juggle.
Definitely. They must ensure safe water distribution, managing everything from the rigorous selection of appropriate water supply pipe materials, a direct echo of Vitruvius's ancient warnings about lead pipes.
Right. Back to Vitruvius.
Exactly. To the precise layout of drainage systems that prevent dangerous backflow and contamination. This discipline, in particular, has those ancient roots, as we discussed. Vitruvius's insights serve as a timeless reminder of the critical importance of material selection for water quality and public health. Now, while modern plumbing has advanced far beyond these ancient practices with new materials, smart technologies, sophisticated waste treatment, the core principle remains the same: delivering safe, clean water and managing waste effectively and hygienically. It's a continuous, evolving commitment to human health. Number 3, the coordination conundrum, weaving the MEP tapestry.
So what does this all mean for the actual building process? We've got these three incredibly complex disciplines: mechanical, electrical, plumbing, each with its own intricate networks, massive equipment, miles of piping and wiring. It sounds like an immense three-dimensional challenge to coordinate all these systems, weaving them together within the tight confines of a building structure, often with steel, concrete, and other structural elements already competing for that precious space.
This is truly where the wizardry comes in, and it's less about magic and more about incredibly meticulous planning, advanced technology, and just relentless problem solving. Imagine standing on a construction site, looking up at a future ceiling space or peering into a wall cavity. That space is meant to house miles of electrical conduit, massive air ducts, complex plumbing lines.
Yeah.
Now, picture that same space already crisscrossed by steel rebar for concrete slabs, structural beams designed to hold up the entire building, maybe even elevator shafts.
Tight squeeze.
It's more than a tight squeeze. The challenge isn't just fitting them in. It's like trying to thread 100 different colored, rigid threads through the eye of a needle simultaneously, each thread needing a precise path, specific clearances, and access for maintenance later on. The BIM handbook highlights this sheer complexity. It notes that large-scale structures involve hundreds of thousands of objects, from the smallest pipe fitting to the largest HVAC unit, that are parts of larger systems. And strict rules determine how these components are organized, often with custom designed and fabricated connections.
So what happens if they clash?
Well, if, for example, a large air duct is routed directly where a crucial structural beam needs to run, or if a major plumbing stack interferes with an elevator shaft, you're looking at massive construction delays, incredibly expensive redesigns, or even compromised structural integrity that impacts safety. It's a huge deal.
That sounds like a massive, high-stakes, three-dimensional puzzle where every piece has to fit perfectly, often with millimeter precision, and all while meeting incredibly strict safety and building standards like fire ratings. Any clash, any miscalculation could be incredibly costly or even dangerous.
It absolutely is, and fire safety is paramount, as the codes meticulously demonstrate. Building Codes Illustrated emphasizes that ducts and air transfer openings passing through fire-rated assemblies like walls or floors designed to contain a fire for a certain duration must be specifically treated. They can't compromise that fire resistance.
How do they do that?
Often it involves installing special fire and smoke dampers that automatically close during an emergency. And these crucial components must always be accessible for maintenance, testing, and resetting later. These are direct MEP considerations that add layers of physical, regulatory, and access complexity. The code also details requirements for fire blocking and draft stopping in concealed spaces with incombustible construction to restrict the rapid spread of fire or movement of hot gases. Again, requires close coordination with MEP system routing.
So MEP and structural teams have to talk constantly.
Constantly. This necessitates incredibly close collaboration between MEP and structural engineers to ensure these elements can be accommodated without weakening the structure or violating fire safety. And Kidder-Parker Architecture and Builder's Handbook further illustrates structural realities. It describes clay, for instance, as an unreliable foundation material due to its plasticity and shrinkage. MEP systems have to contend with that through careful design to prevent displacement of buried pipes or foundation-level equipment. It also details the need for consideration of heavy roof timbers, floor planks, and how MEP elements must integrate without compromising these structural components. Even the structural design's consideration of seismic force-resisting systems, like bearing wall systems or moment-resisting frames, as outlined in Building Codes Illustrated, adds another layer of complexity for MEP routing, especially in earthquake-prone regions where systems need to be flexible and resilient to movement. It's a constant dance between structure and system.
Given this intricate coordination challenge, our sources strongly argue that early collaboration with the MEP team is an essential best practice for creating any high-performance building. Why is that so utterly crucial for these wizards designing the invisible systems? Why can't they just be brought in later in the process to, connect the dots?
Proactive engagement from the outset is not just a best practice. It's absolutely non-negotiable for project success, especially when you're aiming for a truly integrated high-performance building. The PMBOK guide stresses the importance of identifying, analyzing, and proactively engaging with all stakeholders from the start to the end of the project.
Not just talking, but engaging.
Exactly. It's not just about communication, which is merely transmitting information. It's about engagement, which, as the guide says, delves deeper to include awareness of the ideas of others, assimilation of other perspectives, and collective shaping of a shared solution. This means frequent, two-way communication, active listening, encouraging true collaboration through interactive meetings, informal dialogue, knowledge-sharing activities.
So getting them in early changes the design itself.
It can, and it should. Bringing MEP engineers in early allows their critical insights into spatial requirements, potential structural penetrations, the sheer volume of equipment, system loads. All of that can fundamentally influence the core architectural and structural design. This prevents those incredibly costly rework situations, conflicts, and delays that inevitably arise when MEP systems are forced to fit into a predetermined space that simply wasn't designed for them. Imagine trying to install a massive air handler in a space that's already been designed with no access or structural support. It's a nightmare scenario that early input could easily prevent.
So it's really about building genuine relationships and a shared understanding of the project's overarching goals and constraints. It's not just passively passing off plans between different isolated teams. It sounds like true collaborative engineering, working towards a unified vision from day one.
That's exactly right. And this early and deep collaboration also has a direct, profound impact on project costs and schedule. CMAA Construction Management Standards of Practice highlights that proactive cost management during the design phase, with the active participation of the construction manager and timely cost advice, can significantly reduce the need for redesign due to budget overruns.
Makes sense.
And this applies directly to MEP systems, which are often major cost drivers in any building project and have a substantial impact on a building's operational expenses over its entire lifespan. Furthermore, the Practitioner's Guide to Essential Lean Research provides compelling evidence that collaborative behavior can be explicitly fostered by things like integrated project delivery, or IPD, contracts which legally bind all key players to a shared outcome and risk-reward in lean processes. Yeah. They found that practices like motivating, aligning, mentoring teams, along with active onboarding, cultivated high-performing team behaviors because members were supported, encouraged, and rewarded for collaborative approaches to project challenges. So this includes using things like the Last Planner system with its detailed look-ahead planning and pull planning processes to improve workflow reliability and ensure tasks are truly ready and sequenced correctly. It transforms what should be done into what can be done and ultimately what will be done.
So it smooths things out.
Precisely. This integrated approach is a powerful antidote to costly delays, clashes, and redesigns that often plague projects where teams work in silos. It ensures that the invisible tapestry of MEP systems is woven smoothly and efficiently, like cutting edge, sustainability, efficiency, and smart systems.
Now, our episode focus mentions that MEP engineers are at the absolute forefront of the industry's crucial push for sustainability and energy efficiency. How exactly do they contribute to making buildings green? Is it simply about picking energy-efficient appliances, or is there a much deeper, more systemic role involved here?
Oh, it's a huge and increasingly critical aspect of their work. It moves far beyond just superficial greenwashing to truly fundamental design. Sustainable construction defines a green building as one designed, built, operated, and ultimately disposed of in a resource-efficient manner, employing ecologically sound approaches with both human and ecosystem health as primary goals.
Okay, a holistic view.
Very much so. And MEP engineers are absolutely central to achieving prestigious certifications like LEED Leadership in Energy and Environmental Design and Green Globes. These are voluntary third-party rating systems that define, measure, and reward best practices in green building across numerous categories. Their expertise is crucial in specifying, integrating, and optimizing systems that dramatically reduce a building's energy consumption, minimize water usage, and shrink its overall carbon footprint throughout its entire life cycle. They're not just selecting components, they're really orchestrating an entire sustainable ecosystem within the building.
So it sounds like they're not just about making things function, but making them function in an environmentally responsible, long-lasting, and healthy way. It's like they're integral to the fundamental ecological performance of a building, almost its environmental conscience.
Precisely. Their work can involve conducting rigorous whole building life cycle assessments, or LCAs. These are holistic evaluations of a building's environmental impact from cradle to grave, adhering strictly to international standards like ISO 14204.
So beyond just energy bills.
Way beyond. It's about a profound commitment to reducing the building's total environmental footprint, often aiming for a significant reduction, say 10% compared to a reference building. We analyze everything, from the carbon emissions associated with material production, what we call global warming potential, to how the building might contribute to ozone depletion, acidification of ecosystems, or the formation of urban smog.
Wow.
It's about ensuring the building isn't just green in name, but truly minimizes its impact on the planet's entire ecosystem throughout its operational life. This translates into designing incredibly efficient HVAC systems that precisely match building loads, optimizing lighting controls with sophisticated daylight harvesting and occupancy sensors, implementing advanced water recycling systems for gray water and rainwater, and even specifying materials with a lower embodied energy.
Right.
Even aspects like mechanical ventilation for moisture control, like we discussed earlier from the Builder's Guide, contribute to building durability and reduced resource consumption over time by preventing premature material degradation and the need for early replacement.
The episode focus also highlights the increasing technological complexity of their work, with the rise of smart building controls and integrated automation systems. How is technology, particularly powerful digital tools like BIM, fundamentally transforming the way MEP engineers operate and the incredible capabilities they can design into buildings?
The advent of building information modeling, or BIM, is truly revolutionary in this regard. The BIM handbook details how parametric modeling, at its core, allows users to assign layers to wall sections and parametrically lay out nested assemblies for structural, electrical, and piping systems.
So it's more than just a 3D picture.
Oh, much more. It goes far beyond traditional 2D drawings. It creates a live, intelligent 3D model of the building packed with data. This enables the generation of incredibly detailed framing, the derivation of precise cut lumber schedules, which significantly reduces material waste.
That's good.
And, crucially for MEP, precise visualization and coordination of all system components in that integrated 3D environment. BIM tools also support the definition of custom object families that update dynamically according to their context. This lets engineers integrate new custom objects, like specific boiler models or intricate ductwork, with existing predefined elements like walls and slabs, ensuring every piece fits and functions as intended. This level of detail and integration was previously unimaginable. It transforms design from static drawings to dynamic, living models.
This is where it gets truly fascinating, the concept of clash detection and synchronization within BIM. This must be an absolute game changer for coordinating those hidden labyrinth systems we talked about earlier, especially considering the massive challenges of spatial constraints.
It absolutely is a game changer. Perhaps the major benefit of BIM is its ability to identify and resolve spatial clashes. For instance, detecting if a massive duct is running directly through a structural beam, or if an electrical conduit needs to cross a plumbing stack in a way that creates an unbuildable conflict.
Before it happens on site?
Yeah. Exactly. It also flags inter-system connection issues and load transfers, whether energy, structural, electrical, or fluid flow loads among different systems.
Yeah.
This critical clash detection can happen often before construction even begins. It saves immense time, labor, and money by avoiding real-world conflicts on the job site that would otherwise lead to costly rework, delays, and frustrated teams.
Makes perfect sense.
Now, while full automation of synchronization is still evolving, you still need human design decisions and person-to-person collaboration. BIM significantly streamlines this entire coordination process. CMAA Construction Management Standards even recommends having an on-site model and a designated BIM integrator during construction, and using 4D models which integrate the 3D BIM model with the construction schedule for advanced time management.
4D.
Yeah, this allows for clear visualization of deviations from planned sequences and durations, enhancing project control and efficiency. This represents a direct application of the principles of digital fabrication and programmable circuits discussed in Designing Reality. It enables a more direct and efficient way to change the atoms of a building, making it smarter and more adaptable from its very inception.
So, what does this all mean for the smart buildings we're starting to see everywhere, where everything feels connected and responsive, almost alive? How does MEP engineering contribute to that holistic, futuristic vision?
If we connect this to the bigger picture, it moves us directly towards what the city of tomorrow refers to as smart cities and living architecture. MEP engineers are now designing the fundamental infrastructure for dynamic, truly responsive environments that seamlessly integrate sensors, intricate networks, and advanced automation.
Give me an example.
Okay, think intelligent lighting systems that adjust based on occupancy, natural light levels, even individual preferences. Or climate control systems that can be managed and optimized via smart devices. We talked about home heating systems, but imagine an entire office building where HVAC dynamically adjusts zone by zone based on real-time occupancy and external weather conditions.
Wow, really dynamic.
Exactly. This technological leap turns a building into an integrated high-performance machine, constantly optimizing for efficiency, occupant comfort, health, and sustainability. Their work is what allows buildings to not just stand as static objects, but to learn, adapt, and respond in real time. They effectively become an integral, thinking part of a larger, interconnected urban ecosystem. It's an exciting, complex future they are literally building. The engineer's perspective. Beyond blueprints and calculations,
Beyond the complex calculations, the intricate digital models, and the sheer technical expertise, there's obviously a profound human element to this work. A deep satisfaction that truly drives these unsung heroes to dedicate their careers to what is often invisible infrastructure. What's the deeper motivation? The hidden joy, maybe, in shaping our built world in such unseen ways.
Samuel Florman, in The Existential Players of Engineering, describes this profound satisfaction engineers derive really well. It's not merely about solving complex technical problems or crunching numbers, though those are certainly part of it. It's about, as he puts it, the deep satisfaction that stems from an understanding of the world in which we live, and the sheer enjoyment of the neat way in which this physical world is subject to manipulation.
Ah, the joy of making things work.
Precisely. There's a real satisfaction in carrying this chain of events through to its end and seeing the machine jump through the hoop. Imagine an MEP engineer seeing a complex radiant heating system perfectly integrated into a floor, knowing it will provide silent, uniform comfort for decades. Or witnessing a vast air handling unit flawlessly delivering fresh, conditioned air to thousands of occupants. This joy is inextricably intertwined with a powerful sense of obligation fulfilled, the duty to employ their powers for the use and convenience of man, rekindling the ancient joy of helping the tribe to survive. It's about more than just a job. It's about making a tangible, vital contribution to society's fundamental needs for shelter, safety, and well-being.
So these wizards behind the walls are not just technicians then. They're individuals finding deep purpose in making our world function better, safer, and more comfortably, often for the benefit of countless people who will never even know their names or the complex systems they designed. It's a powerful, almost philosophical drive.
Precisely, and this echoes broader architectural philosophy too.
Yeah.
Even Louis H. Sullivan, in the autobiography of an idea, reflects on a childhood dream of power, But not just any power, that power within man to create, to bring forth this sublime, this amazing fabric from nothingness, an almost magical act of transformation. This philosophical underpinning, this inherent drive to build, to optimize, to solve, and to see the tangible results of their intellectual effort is a core motivator for MEP engineers. They're the ones who turn abstract ideas, blueprints, and calculations into tangible, functional reality that directly serves humanity. They transform mere structures into truly habitable, high-performing, and even inspiring environments. It's a quiet mastery, but a mastery nonetheless.
Given the incredible, often invisible complexity of MEP systems, I mean, think about those diagrams with countless line symbols, intricate routings. How do these engineers effectively communicate their designs and intentions? How do they talk to all the various stakeholders on a project, from architects and contractors to clients who might not have a technical background? How do you visualize the unseen and make it comprehensible to everyone?
That's a truly vital question, and it's where engineering meets art and communication. Edward Tufts' The Visual Display of Quantitative Information provides some excellent guiding principles for graphical excellence. He emphasizes that displays must clearly show the data, induce the viewer to think about the substance rather than the design, avoid distorting information, and present many numbers in a small space coherently.
Clarity is key.
Absolutely. This means that complex MEP designs, whether they are intricate flow diagrams for hydronic systems, multi-layered electrical schematics showing power distribution and control logic, or detailed thermal load calculations, must be communicated with absolute clarity, precision, and efficiency. The goal is to demystify the unseen. A well-designed plumbing schematic, for example, tells a clear story of water flow and waste removal, understandable to both a plumber on-site and a project manager reviewing progress. This clarity is paramount for fostering understanding and, critically, for enabling effective collaboration across diverse teams. Without it, misinterpretations can lead to costly errors or even dangerous installations. And this also aligns with the need for clear project progress and financial reporting, as detailed in project management and construction. That stresses the importance of understanding and consistently reporting quantities for cost monitoring. If an MEP design can't be clearly explained, it risks being misunderstood or even incorrectly implemented.
So the ability to represent and explain these intricate systems is just as crucial as designing them. It's about translating highly specialized technical knowledge into a shared language that everyone involved in a project, regardless of their background, can understand and act upon. It's about making the invisible not just visible, but understandable.
It absolutely is. Much like Le Corbusier in Towards a New Architecture, admire the logic and efficiency of the airplane as a model for architectural style, where form is dictated by rigorous function. MEP engineers strive for a similar functional beauty and precision in their designs. And this precision then needs to be conveyed with absolute clarity. It ensures that everyone, from the on-site electrician to the building owner, grasps the nuances of the system. The better these invisible systems are understood by all project participants, the smoother the construction process, the fewer the errors and redesigns, and ultimately, the higher the performance of the final building. This ensures that these out-of-sight systems are never out of mind for those who depend on them for comfort, safety, and functionality every single day. It's really the silent language of building excellence.
Outro. Well, we've journeyed through the intricate, often unseen world of MEP engineers, really, the architects of a building's very vitality. We've explored how their incredible expertise provides everything from heating and cooling to power and sanitation, turning an inert architectural shell into a truly functioning, comfortable, and living environment.
Indeed, they are the technical experts behind the walls, whose meticulous work, from designing incredibly efficient HVAC systems and calculating complex electrical loads to ensuring safe water distribution and waste management, is fundamental to our comfort, safety, and frankly, our modern way of life. Their pivotal role in fostering early collaboration and their leadership in sustainability and technological integration with smart building controls is absolutely essential for creating the high-performance, resilient buildings of today and tomorrow.
It truly makes you appreciate the immense hidden ingenuity that surrounds us every day, silently making our built world function seamlessly. So what's a provocative thought for our listener to mull over as they go about their day? Maybe when they adjust their thermostat, switch on a light, or simply wash their hands.
Okay, here's one. Considering the increasing integration of complex smart building systems and their reliance on digital networks, effectively turning our buildings into massive interconnected computers, what new ethical and security responsibilities might arise for MEP engineers? Responsibilities in ensuring not just the physical functionality and energy efficiency, but also the digital resilience, the cybersecurity, and perhaps even the data privacy of our living architecture for future generations.
A truly powerful thought to ponder as we step further into an increasingly connected world. Thank you for joining us on this deep dive.